Okay, so let's try to understand overfitting a little more carefully. And we'll use a very concrete, easy to visualize, one-dimensional regression setting. Okay. Now, I'm showing two learning scenarios on the right there. We've got a simple, 10th order polynomial target function. So that's in blue in the left picture. And you will observe that none of the data points are on the blue target function. Okay. So what that means is there's a little bit of measurement noise, measurement error. And on the right, we have a complex 50th order target function, and we've generated data, but this time the data is right on the blue target function, so there's no measurement error, there's no noise. Okay. So two learning scenarios. Okay. We have a simple 10th order target function with noise, and we have a complex 50th order target function f with no noise. Okay, so we have two learning scenarios. Now, whenever you come up to a learning scenario, you have to pick a hypothesis set. So I'm going to give you a choice of two hypothesis sets. So second order polynomial fit. Okay. Let's call this H2 for second order polynomial fit, and H10, which is the 10th order polynomial fit. I'll just mention, you might wonder, well, how do I do these polynomial fits? Well, the polynomial fit in regression is just the linear model, okay, with a particular nonlinear transform. So this is just the linear model with the transform that goes from the original augmented input 1x to the quadratic transform, the quadratic transformed x, which is 1x squared. Okay, and in the 10th order polynomial fit, we go from 1x to use the nonlinear 10th order transform. Okay, and this is goes to 1x squared, x cubed, and so on up to x to the 10. Okay, so the 10th order polynomial fit is just, and in general, the qth order polynomial fit just corresponds to a nonlinear polynomial transform. Okay, so you have to pick now. You have to pick either the second order fit or the 10th order polynomial fit. So you have to pick H2 or H10. Okay, and now when we run this class live, I will, ask you guys to decide for each machine learning scenario, you pick the second order fit or the 10th order fit. Okay, so for the simple f with noise, you pick the second order fit or the 10th order fit. For the complex, f with no noise, you pick the second order fit or the 10th order fit. Okay, so, pause the video. 1, 2, 3 seconds. Okay, now if you're coming back, okay, write down, I hope you've written down what your pick is, and now I'm going to go through, plausible justification for the various choices. Okay, so let's start with a simple 10th order target function. Okay, so this is a 10th order target function. I'm telling you that it's a 10th order target function, so it's a no-brainer, right? This is here we have an opportunity to fit the 10th order target function with the 10th order hypothesis. So it seems like, the 10th order polynomial fit should have a good chance of extracting the 10th order target function. So maybe we should choose this guy. Okay. But we saw earlier that, when you add a little bit of noise, it can throw things awry. So the only thing that might perhaps make us go for the second order polynomial fit is that there's a little bit of noise in the data. So noise might, tell us that we might want to, not go for the 10th order complex model. You can think of this as the complex learner. This is the simple learner. Okay, there's the complex learner, and then there's the simple learner. Okay. It's interesting to also think about the second learning scenario on the right, where you have a complex target function, but there's no noise. Okay. Now, here we see that both of our polynomial fits are deficient. There's no way to fit a 50th order, target function with either a 10th order or a second order. Okay. But now we see that, there's no noise in the data. There's no measurement error. Okay. And so, the second order fit is going to have no hope whatsoever. Okay. So, no hope. Okay. And the 10th order fit, while it's still a bit deficient, at least has some chance of getting all the variability of this blue target function. Okay, so we think that this is a no-brainer here. Okay, so in this case, the 10th order fit is a no-brainer because look, you told me the target function is 10th order. So obviously, I should use the 10th order fit. And then here, the 10th order fit is a no-brainer because obviously, there's no noise in the data, so the data is clean, so it's going to give me all the information I need. And why would I go for this second order fit, which has no hope of fitting the 50th order function? Why would I go for that guy instead of the 10th order fit? Okay, so let's see the results. Now, in this particular example, I can synthetically generate the data, I can synthetically repeat the experiment many times, and I can show you what happens. Okay, and there's a sample of what happens. Okay, so when you fit the simple target function with noise, okay, you can either use the second order fit or the 10th order fit. The second order fit is in green, and the 10th order fit is in red. Red because it does very badly. Okay, so this guy, does badly, pretty high error, and you can see the numbers on the right. Okay, and the 10th order fit in this scenario is a total and utter disaster. Okay, but in this case, it's pretty bad. And the interesting thing is my plausible reasoning, that suggested that H2 was probably not the right guy to go for, okay, wins in both cases. Okay, so this was wrong. It's wrong. Okay, so now, let's try to pin it down. And, I said, well, this is a course, and, there's a famous saying that if you're giving a presentation, and your presentation has 20 slides, it's usually the case that, only one of those slides, or at most, as the saying goes, at most, one of the slides in your presentation is where all the money is made, is worth listening to. And if you're lucky, it's exactly one slide, and you should sort of highlight that one slide and say, this is the slide where you need to pay attention. Everything else is sort of peripheral. And now this is a course with 27 or so lectures. And in the same spirit, a few of these lectures are where we're going to really get our money's worth. Okay? And this is one of those lectures. And pay attention. Okay? Because, let me be a little bit careful and slow in what we are saying here. And this is not, my opinion. Okay? We see the data on the right. Okay, so what are we saying here? What we're saying is that, so let's have a conversation between me and my boss, or you and your boss. So your boss comes to you and says, John, I'd like you to learn this target function f. It's a 10th order polynomial representing this, that, and the other. It's a 10th order polynomial. And, you ask your boss, how do you know it's a 10th order polynomial? Well, it's a 10th order polynomial, I'm telling you. We've done the theoretical physics and we know it's a 10th order polynomial. We just don't know the coefficient. Say, okay, good. Okay, well, do you have data? These are the standard questions that you ask as a machine learner. Yes, I have data. Is it accurately measured? No. There's some measurement error. Oh, okay. So, you come to your boss. And what do you tell your boss? You tell your boss, you know what? I'm going to fit your data with a second order polynomial. And your boss is going to look at you and say, what? What? Are you crazy? I told you it's a 10th order polynomial. And you say, well, I'm choosing to fit with the second order polynomial. And your next door neighbor, okay, says, yeah, you told me it's a 10th order polynomial, so I'm going to fit with the 10th order polynomial. So obviously, you get fired. And then your boss goes and gets the 10th order polynomial fit, that red guy on the left, and uses it in practice and gets absolutely slammed. And now thinks, wow, that guy I fired, that guy was going to use the second order fit. Maybe there's something to that. So now, fire the guy who used the 10th order fit, okay, and come back to you, but now you'll ask for twice the salary. And it's because you were able to say something that was so utterly counterintuitive, but it was correct. And that's why this is where the money is, the ability to handle overfitting. What's going on here is that even though you know that the target function is 10th order, it is possible for the 10th order fit to overfit. The 10th order polynomial fit can overfit, even though you know the target function is 10th order. So you are better off ignoring ignoring that knowledge about the target function being 10th order and going with the simpler second order fit. That's what you're telling your boss. Thank you very much. You told me it's 10th order. I'm going to use second order. And if the boss asks you why, it's because you told me there's measurement error, and I'm afraid the 10th order fit might overfit. The 10th order polynomial might overfit. And even though that's the right order, it's too dangerous to use it to learn. That's where the money is. Very counterintuitive. Now, we saw earlier that if there was no noise in the data, okay, the 5th order polynomial would get exactly the target function. Okay, so you're reasoning along the same lines, okay, with your boss, let's say, in the room. You know what? If it was a 10th order target function with no noise, I would certainly use the 10th order fit. The boss says, yeah, that makes sense. There's no noise. The 10th order fit will exactly capture, it's uniquely determined as long as I have at least 11 data points. It's uniquely captured by the 11 data points. I can uniquely pin down a 10th order polynomial. And so if there's no noise, you'll get me the target function. Yes. Okay, good. So you and your boss agree that if the target function you were trying to fit was 10th order with no noise, you'd go with the 10th order fit. And then the boss says, wait a minute, I just called up engineering. And engineering just told me they found a bug in their derivation. The target function is not a 10th order polynomial. It's a 50th order polynomial. But still, yes, they can get perfectly accurate measurements. It's now a 50th order polynomial with no noise. So you look at the boss and you say, that's interesting. Well, in that case, now that the target function has gotten more complex, I'm going with the simpler model, the simpler second order polynomial. And the boss looks at you and says, are you smoking something? What? We agreed that if the target function is 10th order with no noise, you'd go with the 10th order fit. Now I'm telling you the target function is 50th order, and you're going with the second order fit. I say, yes, because we only have 14, we only have 13, 14 data points, so I'm going with the second order fit, even though we agreed that with 10th order target function, I would go with the 10th order fit. And the boss is looking at you, and let's see, why is what you're saying so counterintuitive? The target function has got more complicated, and it's better to go with the less complicated hypothesis. What? Okay, at this point, you should be saying to yourself, what? You should be reeling backwards, falling over. I mean, it's completely counterintuitive. And all of this has to do with overfitting. Okay. So basically what's going on here is that even though the target function got more complex, you are now getting less complex as the learner. Very counterintuitive. So your boss tells you the target function order, you don't use the order of the target function, even though it's available to you. Your boss tells you the target function is getting more complex, you are becoming less complex as a learner. And that turns out to be better. Depends, of course, on the number of data points. And that's what we're going to investigate. Okay. But before we get there, I just want to show you that I kind of pulled a con on you. Okay. So I showed you, two learning scenarios. Okay. What were the two learning scenarios? Simple F with no noise and, complex F with simple F with noise and complex F with no noise. I'm repeating those two scenarios there. And then you had to make a choice between a simple hypothesis set and a complex hypothesis set. Okay, so what's the con? There's no con. The con is that I deliberately showed you the target function, okay, which then I identified for you that, on the left there's measurement error and on the right there's no measurement error. Okay, and showing you the target function was the con. You say, what? How can it be a con? That can only help me. No, because, in practice, you don't get to see the target function. You don't get to see the target function. You only get to see the data. Now, by showing you the target function, you were able to identify, there's measurement noise on the left and it's perfectly pure data on the right. But in practice, you can't tell the difference between the left and the right. You don't know if the left is a complex target function with no noise or a simple target function with noise. Same thing on the right. Look at the data that you would see when you approach the problem as a machine learner. That's what you would see. And you can't tell whether there's noise or not, and whether the target function is simple with noise or complex with no noise. So actually, both of these learning scenarios, when you look just at the data, are very similar learning scenarios. And as the learner, you cannot tell the difference between the two. So it's actually no surprise that in both cases, it's the same model that wins. And what matters is not that you match your hypothesis set to the target function. What matters is that you match your learning, your hypothesis set, to the data. It's the data that matters. That's important. That it's not the target function that you should be worried about. It's the data, the quantity and the quality of the data. That's what should determine what you do. Okay? Not this sort of peripheral information about the target function. All right. So, we're going to study overfitting now. We're going to now try to pin it down a little more. Okay, now we saw this illustrative example. And so, let's define a measure of overfitting. Okay, in this context of second order and 10th order fits. Okay, and then we'll go to the slides and see some real data, some real pictures, and stay tuned because I'm going to show you the pictures today that are in some sense a logo for this course. Okay? And the pictures that you're going to see today are from real data. And they are the pictures on the front of the book. Okay? And so, if these are the pictures that are making the front of the book, we had a reason for choosing that. Those are very important pictures. And they're going to make an appearance today. So it's a star-studded lecture. Okay, so let's talk about overfitting now. Try to now make it a little more quantitative. Okay, so we saw these very stunning conclusions. You know the target function order, yet you may choose a simpler hypothesis set. The target function got more complex, you go simpler as the learner. Wow, imagine standing up and telling this to your boss. They'll think you're crazy, and then they'll have to pay you double when they get, messed up by not following the expert who knows how to handle overfitting. Okay. So, the overfit measure, an overfit measure. Okay. So we know that for H2, the second order fit, and if we compare H10, okay, so you have E in of H2, whatever in-sample error this guy can attain, is going to always be at least as large as E in of H10. Okay, so it's always the case that if you go for H10, you're going for the better fit. You're going for the lower in-sample error. Okay, so if E out of H10 is greater than E in of H10, then we have overfit, right? Because E out of H10 is greater than E out of H2, then we have overfit, right? Because we went for the lower in-sample error, okay, and got a higher out-of-sample error. So we fit the data more than warranted. Okay, so we can define an overfit measure, which quantifies how much we have overfit. We'll define an overfit measure, which is just E out of H10 minus E in of H10. Okay. And the higher this number is, the more the overfitting. The lower this number is, the less the overfitting. Okay. So now let's go to the slides, and I'm going to show you some curves where we study this number. So, some of the parameters that we can, mess around with in our sample scenarios, and we can do this, because we are generating these, they are artificially generated sample scenarios, but they're still real data, just that, we control the scenario. Okay, so we can control, what can we control? Okay, so we can control the amount of measurement error. So the noise, let's call that noise, or measurement error. Let's call that sigma squared. Okay, the variance in the measurement errors. Okay, and the larger the noise, the larger the measurement errors. Okay, we can certainly control the number of data points. Number of data points. Okay, so n. And we can control also in this scenario, because we are generating the data and the target function, we can control the complexity of the target function. We can control the complexity of f, the target function. So, and one way to quantify that is the degree of the polynomial q. Okay, so this is the degree of f, the degree of the polynomial, we can call it q. Okay. So what we're going to do is we're going to generate a variety of scenarios, learning scenarios, where we systematically vary the noise, the number of data points, and the complexity of the target function. And let's see, when does overfitting occur? Okay. So we can compute this overfit measure and see when does overfitting occur. So let's erase the board. Well, let's move to the slides. Okay. Okay, so first, let's vary on the x-axis the number of data points. Okay. And on the y-axis, we've got this noise level that I talked about. Okay, so noise increasing, number of data points increasing, and for each choice of the number of data points and the noise level, we will assume that the target complexity has remained constant. And what I'm showing in a color-coded way is the overfit measure. And red means higher, blue means lower. Okay, and it's very easy to see a pattern here. Okay, which is that as you have more and more data points, you move from the red region to the blue region. So more data results in lower overfitting. Okay. If you fix the number of data points that's at 100 and start increasing the noise, the overfit measure gradually increases and eventually flips over to positive, which means you're overfitting. So this deep red region is the region of severe overfitting, and this blue region is the region where there's no overfitting. So in the deep red region, you'd rather choose your H2, your second order fit, over the 10th order fit. And in the blue region, you would rather choose your 10th order fit over your second order fit. So let's summarize. When you have a small number of data points, okay, almost independent of the noise level, go with the simpler fit, okay, H2. When you have a large number of data points, okay, in this region, okay, as long as the noise level is small, you can go with your more complex 10th order fit. Okay, but as you increase the amount of noise, get ready to shift over to your second order fit. So more data points overfitting down, more noise overfitting up. And, that we might say is sort of what we expected from intuition and maybe, folklore or knowledge. Okay? And here I'm showing it to you in this beautifully, color-coded image. And like I said, okay, this image is one of the headline images. It's on the front, it's on the front of the book. It's a very important image, which says that get ready to switch over from the more complex model to the simpler model, when your number of data points goes down, or the amount of noise in your data goes up, and it's sort of you get the same picture no matter what the complexity of the target function. So even if the target function has 10th order polynomial complexity, you still will switch over to the second order polynomial for a small number of data points and a high enough noise. Okay. Now, let's vary the number of data points and the target complexity to see how the target complexity affects things. And we get the second picture that's, on the front cover of the book. So these two pictures are very important. And you see a very similar picture in terms of where is the blue and where is the red. Now, these nice linear, color-coded regions is due to the fact of the linear model and the way noise affects the out-of-sample error. Here we have the target complexity, and you still have these red regions and the blue regions, similarly, positioned. Okay, and the message is still the same. Okay, that if you have more and more data points, you get into this blue region, and you can afford to pick the 10th order polynomial fit, for various degrees of complexity for the target function. But as you have fewer and fewer data points, and in this case, we've kept the noise level is fixed. As you have fewer and fewer data points, get ready to switch to the simpler second order polynomial. Okay? And that doesn't really matter whether you're dealing with a very complex target function like 100th order or 25th order. Okay? And basically, as you have, let's say you have 80 data points and a 25th order target function, you still go for the simpler fit, even though it has no hope of fitting a 25th order target function. It's deep red region, lots of overfitting. The second order polynomial fit is significantly preferred. Okay. So what's the message here? The message here is that, as the target complexity goes up, here is a very counterintuitive message. As the target complexity goes up, you should prefer the simpler model. Imagine telling that to your boss. Boss, since the target complexity is going up, I'm switching from the 10th order fit to the 2nd order fit. What? Yes. To avoid overfitting. And this is not conjecture. This is concrete. This is quantitative. The overfit measure has gone into deep red territory, okay, as the target complexity goes up. Okay. And so, what we're going to try to do is now understand why these two pictures are so similar. Okay. And in doing so, we're going to unify the target complexity with the noise level. Okay. So let's go back to the board.